All right, microwaves are also a type of radio wave. They are used in microwave ovens, obviously. And we're going to show you a little demonstration in a couple minutes on how microwaves actually work and how you can actually measure a microwave. And they're also used by cell phones and pagers, and they're used by radar. Radar stands for radio detection and ranging devices, and you've probably had experience with those. If you've ever sped and had one of the state policemen or one of the local cops pull you over, they used a radar. Actually sent out a radio wave, it bounced back to them, and they were able on their little speed gun to figure out how fast you were going in that school zone. Our next electromagnetic wave that we want to talk about is infrared. Infrared actually means below red. So it helps you to keep them in order, because when you actually take your ECA, your end of course assessment, or you take a test on waves, you need to get the electromagnetic waves in order from largest wavelength to shortest wavelength, or from least frequent to more frequent. So this is one way to help you do that. Infrared means below red. So obviously visible light, starting with red, would be the next wave that we talk about. So they're shorter in wavelength and higher frequency than microwaves. Something that you're probably familiar with, anything that causes you to feel some warmth, that is usually infrared. Heat lamps, warm objects. You probably have seen a thermogram, even if you didn't know that's what it was called. Anytime, and the military uses these a lot, where they have heat-seeking missiles, or they have night vision goggles, that actually creates a thermogram where they can pick up different temperatures of everything that's surrounding them. And by that, they can figure out where people are, where trucks are that have just been turned off, and they can use it in that way. So this is an example of where you can actually see some infrared. So we're going to talk about visible light. Visible light, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. You need to make sure you know that. They are the only electromagnetic waves that we can actually see. And they're the longest wavelength is red, the shortest would be the violet or the purple. And anytime that it enters a medium, it bends, which if you remember, we talked about reflection and refraction. Okay, that means that there is a bending, and each wavelength bends in a different way. That's what causes us to be able to see rainbows. And this shows you an example of how it all bends. And if you notice here at the bottom, you will see that each color of visible light bends at a different angle, has a different refraction. Ultraviolet. Now, ultraviolet actually means after violet. So infrared means before red, ultraviolet means after violet, and in between is Roy G. Biv. So ultraviolet, once again, we're getting shorter with a higher frequency. Ultraviolet are used quite a bit in doctors' and dentists' office. They use them to kill bacteria, and they actually put them in to a little machine, and they can sterilize all their equipment that they use. Ultraviolet rays can be good and bad. They help us to produce vitamin D. They can help to treat jaundice. But if you get too much sunlight, including too much sunlight in tanning beds, it can cause you to have skin cancer. So it is recommended that you never go outside with anything less than a SPF 45 sunblock. Then we'll talk about X-rays. You're probably familiar with X-rays. Once again, higher frequency, shorter wavelength. And they have a lot of energy, and they can penetrate most matter. Now, the reason we use them, if you've been to the dentist recently, if you've broken a bone or sprained an ankle, they'll take an X-ray, because X-rays are absorbed by bones and teeth, but they actually go through the soft matter. So that's why we can very easily see what's going on with your bones and your teeth. So we take x-rays. Too much exposure, though, can cause cancer. So that's why dentists put that lead-lined vest on you, or anytime you go to get an x-ray, they possibly put some kind of lead on you. That's why the x-ray technician walks behind a wall or outside the room. That would be a lead-lined wall to help them to not have so much exposure to x-rays. And we also use x-rays. Engineers use them, they x-ray welds to make sure that they're going to hold. They x-ray for cracks. They just had some bridges here in Idaho that they went and looked at, and they x-rayed them and found that there were cracks, and they're going to have to close them and replace the bridges so that no one gets hurt. So engineers use them a lot to make sure that the structures that we have keep us safe. An example of an x-ray, there you go, a wonderful bat. It shows you how all the soft tissue, it goes right through. We can't actually see the organs, but we can see all the bones, and we can actually go through the wing, but we can see what holds the bones that hold it together. So x-rays are really useful. And finally, we get to gamma radiation. Okay? So gamma radiation, or gamma rays, they're the highest frequency of electromagnetic waves, which means they also carry the greatest amount of energy. They can penetrate the most, they can do the most good, and can do the most damage. If you ever hear of anybody having a radiation treatment for cancer, that's exactly what they're doing. They're zapping them with gamma waves. It's very, very harmful if it's not used correctly, and my father actually had a brain tumor, and they used radiation treatments on the tumor after they had operated because they couldn't get it all, and it was in his brain stem. And what actually happened was he had about a golf ball sized place on the back of his head where the radiation not only killed the cancer inside his brain, but it killed all the hair follicles, so hair would never grow in that spot again. And he said it was like having the absolute worst sunburn you could ever imagine having. So that's gamma radiation. So we can use electromagnetic waves to actually observe different things. We're really interested in it when we are trying to look at the stars, because we can put different filters on, and you can see how this very same picture looks completely different depending on which wave we are looking at. So there's radio, infrared, ultraviolet, X-ray, and gamma. So that just gives you an idea of the interesting things that we can look at. So I need to do just a little quick summary. All electromagnetic waves, regardless of their frequency, travel at exactly the same speed. Everything from radio to gamma travels at the same speed. They all have different wavelengths and frequencies. Once again, that inverse relationship. If it has a long wavelength, it has a low frequency. Short wavelength, high frequency. And the higher the frequency, the higher the energy. Now, in case you don't remember what I'm talking about, if you've got a wave that actually looks like this, whoops, there we go. Those are kind of ugly waves, but anyway, right here is called equilibrium. If you will notice, here is a wavelength, and here is a wavelength. When you look at the frequency of the longer wavelength, 1, 2, 3, 4 hertz. Shorter wavelength, 1, 2, 3, 4, 5, 6 hertz. So a shorter wavelength has a higher frequency, which means there's more of them, and it will have higher energy. So that's our electromagnetic spectrum. Actually, we have a little exercise for you to do. So I hope you enjoyed this, and I hope that you have a little more basic knowledge of electromagnetic spectrum. And if you have any additional questions, please refer to Chapter 12 in the book.